We're starting now to study implicit differentiation. And we're going to use implicit differentiation when it's difficult for us to isolate y. So if y is all alone, in this case, we're going to use explicit differentiation, which is our normal differentiation that we've used all along. The derivative of y, this is going to be very important for us later, is dy dx, and we're just going to use explicit differentiation. Again, that's our normal differentiation using the power rule for x to the third, multiply and subtract, minus 8, and we get our derivative there. I guess the most important thing here to recognize is when we have y, when we take the derivative of y, we get dy dx. Again, we're asking, should we use explicit differentiation or implicit? And here, again, it's fairly easy for us if we divide both sides by 8, or, as I like to do, multiply both sides by the reciprocal of 8 to get y equals 1/8 x. It was very easy for us to get y all alone. So the derivative of y, again, probably the most important thing from this board, is dy dx. And this is our explicit, or doing it the normal way. What we've done up to this point in the course is do explicit differentiation, because y, we could always get it all alone. Again, we're asking implicit or explicit. Now, look at all the hoops I would have to jump through to get y all alone here. If you're strong in algebra, and I know you are, subtract x squared from both sides, multiply each and every term by -1, so we can change the sign of each and every term here. So this will be +9. And now I'd have to get y all alone, I'll have to take plus or minus the square root of x squared minus 9x plus 9. And I'm at a loss. I don't have any rules for this, dealing with this plus or minus. Apparently, well, actually, I could really do this, couldn't I? I could take the derivative of this once, saying that this is x squared minus 9x plus 9 to the 1/2 power, and then I do it again for the negative root. But that seems like an awful lot of work compared to our new method, which will be implicit differentiation. It was going to be a little bit difficult for me to find the derivative explicitly, because I would have had to jump through a few hoops to get y all alone. Look how much easier it will be to take this through implicit means. So what do I do for implicit differentiation? I'm going to, if I have an x, I'm going to treat it like normal explicit differentiation, 2x to the first, minus, I'm going to do the same thing with the y, 2y to the first. Now look, I'm using the power rule, multiply and subtract. The only difference here is we're going to use the chain rule with the y. So what is if we put y here in parentheses, multiply and subtract, now here's the chain rule. Take the derivative of whatever's in parentheses. And we just established earlier that the derivative of y is dy dx is equal to 9. And remember that this is x to the 0. So when I multiply and subtract with a constant, I get 0. By the way, just a little review as well. I have a 1 here, so when I multiply and subtract, I just get the coefficient of the linear term becomes its derivative. Algebra skill time. I need to isolate the dy dx. I have to get this all alone. So the first thing I'll do is I'll subtract 2x from both sides. So I have -2y times dy dx is equal to -2x plus 9. Now, because I have multiplication here, I'll divide both sides by my -2y. So I hope this is familiar to you from all of your days with algebra. And here we have our derivative, dy dx. Now, often when we take dy dx through implicit means, our derivative is in terms of both the variable x and the variable y, as you see it here. If we had finished that explicit differentiation earlier, where we isolated y with the plus or minus root, then we would have had dy dx in terms of x alone, but now we've got it in terms of x and y. The implication of that is if you're asked for the slope of the tangent line, you have to be able to substitute for both x and y, not just x alone.